Hi, welcome to another edition of Calculus 2. We are going to continue our conversation about numerical integration at a higher level than the previous lecture. Let's go ahead and see what this was about. So, our idea was that we want to estimate an integral, a definite integral from a to b of f of x dx. We want to estimate that. We talked about y estimation as opposed to exact answer. We said in most cases an exact answer is not available. We have to go to plan B, and plan B was to find an approximate value. So the idea was, well, the definite integral is equal to area under the curve, and we want to approximate this, and the natural thing is to divide it up to regions that look like something we can calculate the area for. Easiest thing to divide this thing into would be rectangles. The area of rectangle is the easiest one. So we go ahead and cut this up into a series of panels and then approximate the area of those panels and add them up. So before we go into the formulas and things of that sort, let's go ahead and take a look at a few pictures to make sure we understand what we are after. And then the formulas themselves look rather lengthy or perhaps scary or something, but they are actually extremely simple. It's just repetitive addition, not much more. Okay, so here is a little demo on Desmos website where we are approximating the area under a curve by the methods we talked about last time. So we have some curve here, some function. You can type in anything you want, and then this is the graph of that function. We want to calculate the area under this graph from some location to some other location. So here where we are specifying beginning of the region, for example, at 1, end of the region is at 8, and then we want to calculate this area. So we go ahead and divide this to several panels. Here I've conveniently divided to 7 panels, so the division lines are right on top of the whole numbers and picture looks clean. We have colored these panels in alternate colors so that you can tell them apart from each other. We want to figure out the area of these panels and add them up. That's going to be an approximation for the area. Why an approximation? Because, well, we want to calculate the area underneath the curve, and when you approximate it by this rectangle, you're missing this white portion. So this purple portion is missing that one. Here this yellow portion again missing a piece. So for this curve that happens to be increasing, this style of calculating the area is going to underestimate it because we are missing all these pieces. Well, what if you want to improve your approximation? Well, it's easy. You just increase the number of panels that you have, and you get a sense that the total area that is not being colored is actually decreasing as you increase the number of panels. So if I go way up, then the amount that is not colored, the white region, is shrinking towards 0, and the total that I obtain is going to be close to the exact answer. Well, yeah, are we getting free lunch here? No. Well, you have to work a lot harder to add up 27 pieces as opposed to what we had at the beginning, which was like 7 pieces. So the more approximation the better approximation you want, the more rectangles you need and the more work you need to do. So the name of the game is essentially how quickly and how efficiently you come close to your target. So you remember last time we talked about several methods for doing this thing. We talked about left rule, right rule, mid rule, trapezoid, Simpson, and so on. And today we are going to talk about that more extensively and just go look at some examples. So this is an example of a left rule. We are calculating these areas built on top of the height on the left of each of these panels. Well, the method here for going to the right rule is just to switch this parameter. If I go to here, when my c is equal to 1, this is just a parameter to adjust your shape. The rectangles are all built on the point at the right corner. So in this case, you see that our areas are exceeding what we want, and for this situation we are overestimating the area if we add these things. Well, what was the other item we had? We also talked about the trapezoid rule. So trapezoid rule, midpoint rule. We talked about the midpoint rule. Midpoint was in each of these panels, we go to the middle point and make our rectangle at that point. The advantage of midpoint that we see right away is that there is a bit of overestimation here and a bit of underestimation here, and these two are very close to each other, so they are going to cancel each other out, and we are going to get an answer that is significantly better than either the left. This was the left rule. You see, obviously we are missing quite a bit. We are underestimating all over the place. If I switch to the right, I'm overestimating all over the place. And if I do the middle, I'm doing half underestimation, half overestimation, and it's a very good chance that they are going to be nearly canceling each other out, not quite, but closely following each other and canceling each other out. So midpoint rule, even though the number of calculations you do is exactly the same as left or right, it is significantly superior to either left or right. So those are the issues that we said comes up in a course called numerical analysis. You should look at this issue in much more detail. Now we said out of left and right there was another option we had, which was the so-called trapezoid rule. Trapezoid rule, you look at each of these panels and approximate each panel by a trapezoid. You simply connect the two endpoints here. Let me blow this thing up so that you see perhaps sorry. You see that straight line here is the side of the trapezoid, and the curve now is underneath it. And let's just go ahead and blow this up some more. Perhaps you see it better this way. So it's going to be an extra long trapezoid, but you see I'm connecting this point to this point by a straight line. So I'm building a trapezoid. The curve could be below it, could be above it. So we see that the amount of error that we are making here is substantially less than it was with left or right. In fact, it turns out to be comparable to the midpoint rule. We are going to talk about the amount of error of each of these methods, but here what we wanted to show is what will happen. The best of the class for the methods that we had was the Simpson rule. Simpson's rule is when you approximate your curve by a parabola, essentially, and you calculate the area underneath that. When you approximate your curve by a high power polynomial, then your approximation improves and then you get a better answer. And we are going to talk about the Simpson method as well. So Simpson method, what's happening here is that this segment is being approximated by a parabola. In that case, we actually have a midpoint here, a point here, and a point here. we pass a parabola through all three of them and calculate the area underneath that, and that's what we are counting as the approximate area. Okay, so that is what we have in mind. Now let's go ahead and look at the mathematical details of it. Okay, so we want to approximate this integral. There's a beginning and an end, so a and b are the end of the interval. There are certain number of panels. In that picture we saw, let's go back to this thing. Let me go back to the original picture, and let's go. So this was, you remember, this was midpoint, left, right, and so on. So it's clear that we have a certain number of panels in mind. How do we handle this? So I have a A, I have a B, and I have a N. Here is written as a capital N. In my lecture it's going to be lowercase n. So we take the distance from B to A, that's this entire range, divided by how many panels we want, and that's going to tell us what's the increment or what's the width of each of these panels. So that's what we are going to do here. We are going to so we take the distance from B to A, that's the overall base here, divided by number of panels we want. This ratio customarily is referred to as H or delta X. These are kind of traditional lettering to use to indicate the width of these panels. And then what? Well, each panel has a beginning and as an end. I'm labeling it here as x0, x1, x2, x3, and if you have n panels, the last of these is going to be x sub n. One thing to get used to is that the very first one is x sub 0 in this notation. Okay, for future use, I'm also pinpointing what's the midpoint of these areas. I'm calling them M1, M2, M3, and so on. The height on top of each of these endpoints, x0, x1, x2, they are being indicated as y0, y1, y2. So y with a certain index is f applied at x with the same index. Let me just show you on the picture again to make sure we are all on the same page. So this will be x, this point here is going to be x0, x1, x2, x3, x4, x5, x6, x7. So the label of the last point is the number of panels you have. So at x0 we go up. Let me go to my left point rule so that's clear. So at x0 you go up until you hit the curve. That's your y0. That's f applied at x0. Next one, this is x, this point is x1, and this length is f of x1, which we are calling it y1. This is x2, this is going to be y2, and this is x3, and this whole thing is going to be y3, and so on. So the notation is a little bit crowded, but there isn't really advanced arithmetic or advanced calculus or anything here. The operation is going to be very simple. So what do? We want to calculate the areas of these panels. So how do you calculate the area? You calculate base times height. Is that right? Well, base is the same. Thankfully we made it same in our calculation just so that our formula is going to look simple. So we are going to be factoring the base and then adding up all the heights. So really the first panel is h times y0, second panel is h times y1, and the last of these is going to be h times yn sub 1, n minus 1. That is for the left rule. Again, let me remind you the difference between the left and right. So in the left rule, let's shrink this a bit. Let's see, maybe. So we take the base is the width of all of these rectangles. The heights are changing. Here's a height number 0, height number 1, height number 2, and so on. This is height number 7, that is y7. I have to take each of these heights and multiply by the base and just add them all up. I can go ahead and factor the width of the base and then multiply by the sum of all the y's if I want. That's an option I have. Makes my formula a little bit less crowded. So that's what this formula really is saying. Base times height, base times another height, base times the very last height, you have to add them up. Okay, that's the left rule. What was the right rule? You do the exact same thing, except that you skip the very first starting y value. You start at y1 and then you go all the way to the last y value, that's going to be y sub n. Let me show you in the picture again to make sure. This is just the main idea is so if I want to do right panel, let's shrink this a bit maybe. So when we are doing the right panel, the very first height is y sub 1. We are skipping y0 and now it's y1 all the way to the very last one, which is going to be labeled as y sub n. We multiply all of them with our bases and add them up, and the formula turns out to be just what we wrote down here. So in the L rule we are missing the very last y. In the R rule we are missing the very first y. What was the trapezoid rule? Trapezoid rule was just average of these two. Average of these, well, if you average y0 and nothing here, it becomes y0 over 2, and the last one also doesn't double up, so it becomes yn divided by 2. So I separated them, and then y1 plus y1 over 2, that's just y1, and so on. This is the formula that is written here is a smarter version of what might show up some other places, which could be like this. Sometimes the formula is written in this way as y0 plus 2y1 plus 2y2, and so on we go until 2yn minus 1, and then we come to yn. This looks nicer than that, but as soon as you start using it in practice, you notice that you are wasting a lot of effort. Well, what waste is here? You're doubling all the way, and then you're dividing by 2. Of course, doubling and division are going to cancel each other out. These type of calculations tend to be kind of lengthy and tedious, and adding to your calculation is never to your advantage. So you always try to find shortcuts to make the process take less time. So if efficiency is a issue for you, then you go after a version of the formula that doesn't waste calculation time. So this is one such way, one way of writing that kind of approach. And then we had the midpoint rule. Midpoint, we said the heights are evaluated at the midpoint of each panel. Let's go ahead and take a quick look at that also. So mid panel, this was an example of that. Let me just blow it up. So in each panel we go find the middle point, find the height there, then find the height that next one, and so on. Take each of these heights and multiply by the base and add them up. That's what the formula really refers to. So again, the base is common, we factor it out and multiply by height of the function at the midpoint. So midpoint here, I'm calling it m1, m2, m3 all the way to mn, and each of these midpoints, if you want to have a formula for it, could be the right end of the panel minus half of the width. That's going to bring you to the midpoint. But in a typical calculation, it's much easier to just follow step by step and figure out all the m's. Okay. The more advanced of these rules was the Simpson's rule. Simpson's rule, I guess I'm missing an S here. Simpson's rule. To begin with, we need to have the n must be an even number so that we can allocate 2 of each subpanels for a parabola, and then our formula is going to work out. So last time in the previous lecture I gave you a recipe for Simpson rule, which was based on the trapezoid and midpoint. Let me just go take you back to this one. You remember that we said, well, you have left and right and midpoint. Trapezoid was the average of these two, and a Simpson rule was a particular average of these, twice the midpoint and one of the trapezoid. You create this kind of mixture, divide by 3, and that's essentially what Simpson's method, I'm missing an S here also, Simpson's rule turns out to be. So if you want to follow the formula that typically shows up in most text, which does not rely on these things, just straightforward and goes and calculates what S is going to be. So first we pay attention that n must be even, and then, well, we have this particular or peculiar looking formula. The first and the last heights, the coefficient are 1. Then all the odd numbered heights, the coefficient is 4. All the even number heights, they are going to have a coefficient of 2. So if you want, you can say first and last, they just show up as themselves. Then y1, y3, y5, all the ones with odd indices get multiplied by 4, and all the ones with even indices get multiplied by 2, and then all of this has to be multiplied by h over 3 to get your Simpson rule. Let's go ahead and actually write this thing out for a particular case. Suppose I have a function. F of x. Let's write something maybe 1 over, say, cube root of x plus 1. Okay, so if I want to calculate this integral, say from 1 to 9 of f of x dx, so if you want to approximate the integral, which is given by this, by using Simpson's rule with, okay, you remember we said the number of panels has to be even, and here, just to make our numbers come out nice and easy, with 8 panels. So if I'm going from, so if I'm starting point is 1, the ending point, let me 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I'm going to allocate, the very first one is going to be x0, x1, x2, x3, x4, x5, x6, x7, x8. In this friendly example, these x's are just the whole numbers. They typically we don't get to be that lucky all the time, but here, just so that we're not creating too much of a bother with also the fractional numbers and such. Okay, what do we want to do? First, we want to say age is ending point minus beginning point divided by the number of panels. That's going to be, thankfully, just a nice number is 1. The integral I want to calculate by this approximation is going to be this age divided by 3, so it's 1/3 of. Then what we do is that the first and last point are going to have coefficient of 1. Then starting from this second entry, the coefficient is going to be 4, and starting from this one, the coefficient is going to be 2, so we jump. And then what we have now is, so these are going to be my coefficients. Let me write them all down. So it goes with 1, 4, 2, 4, 2, 4. So how many 4s do we need? 1, 2, 3, 4. Is that right? So I'm missing 1. And the last one is just going to be 1. Of what? Well, I have to calculate this function at these x values. My very first one is just 1, so I take the 1 and plug it here. So it's going to be 1 over cube root of 1 plus 1 plus next x value. These are my x values. These are x values, these are the coefficients. Next x value is 2. I take the 2 and put it here, so 1 over 4 cube root of 2 plus 1, and then plus next x value is of course 3, so 1 over cube root of 3 plus 1. This, we are going to be adding all of these things, of course, so let me put my plus signs. And then who's next? What do you think I should write here? So maybe we bring our pretty picture here to gives us some incentive to think about. Okay, so that is a cue that you are going to tell me what is it that I'm going to put here. Is that right? That is what this picture is for. So of course 1, 2, 3, this one is going to be just 4 cube root of 4 plus 1, and here I'm going to have what? 1 over, should we pull out a nice picture again? So what's that? Cube root of 5 plus 1. I needed to allocate more space here. Cube root of 6 plus 1, and cube root of 7 plus 1, 1 over cube root of 8. The 1 is outside, is that right? And then the last point is just a cube root of 9 plus 1. Well, now we have to type in all of these things in our calculator and then add them all up, and of course that is going to be by itself a task. That's why people usually use a computer for doing this. Most of the problems you come across in calculator or in your homework, the work that you have to do here is not as much as what is here, but you can see that the task is repetitive. So if you have a computer, you can calculate this thing rather quickly, and then that's how you get your approximation. Okay, now last topic for today, we are going to talk about error estimate for these formulas, and that's going to close the topic. Now all the formulas that we are going to write right now, essentially none of them we can prove right now. because they require an approach that's going to come up later on in the course, namely Taylor series theorem. But here we are just going to indicate a general idea. The question is, what is the amount of error that we are going to commit by using these formulas? Again, let me remind you, let's go back to this case where the error is very clear. Error is going to be the total amount that is not painted here. As you see in this left rule, for this increasing function, if I add up all these areas that are not painted, I'm getting my total error. The question is, when you are using an approximation, you want to have an idea how good your approximation happens to be. Error estimates are a device for getting a handle on how big of an error you have in a certain calculation. So all professional mathematical calculations always have an error estimate next to them. For our problem, for the area calculation, we said we had the left point rule, right point rule, then we had the mid rule, trapezoid, and the Simpson. So if in each of these cases we want to calculate the error as for example, the exact value minus the approximate value. So if we, in each case, if we calculate this thing and show that by error of the method, so I have error of the method L, I have the error of R, I have the error of M, I have the error of T, I have the error of S. These are all different. When we looked at those pictures, you remember that the left and right, one was underestimating, the other one was overestimating. So that means if you actually go ahead and calculate EL and ER, they are going to have different signs. If one is over, the other one is under, then one's going to be positive, the other one's going to be negative. These two also, in general, they have opposite signs. We don't have a pair for this one right now, but the idea of error estimate is to give a handle on how big this number is going to be. It could be positive or negative, so we put this in absolute value, and the question is, how big can this thing be? You can sense that if the area of the integration is bigger, then you are going to make bigger error. That is, if a minus b is big, then you suspect that you will accumulate more error. But how does it depend on that? It all depends what kind of method you are going to use. And of course, we talked about the role of number of panels in any of these cases. If you increase the number of panels, then you decrease the amount of error that you have. Finally, these errors depend on how much turn and twist this function is going to have. If your function is tamed like a straight line, your error is going to be small. If the function waves around quite a bit, your error gets to be bigger. So the error is going to depend on the derivatives of this function. The exact detail of it, we have to wait until we cover Taylor series theorem. But error of the left method is at most it is b minus a, that is the length of the area, the length of the base squared, divided by 2 times the number of panels that you have, and something that's going to indicate how steep your function is. So that's going to be the derivative of the function that you have. So max of this derivative is going to control how big of an error you're going to have. For the right is the same in absolute values, exactly the same, even though without absolute value they are going to have opposite signs. So that's also b minus a squared over 2n and it's exact same thing here. It's exact same formula, but the e's are going to be of opposite sides. For the midpoint and the trapezoid, for midpoint this is going to be b minus a cubed over 24 n squared, and it's going to depend on how high the second derivative is going to be. For the trapezoid method, opposite sign is this, and twice as much error in this and that compared to that one, so that's b minus a cubed over 12n squared, and then again maximum value of the second derivative. This maximum value is always on the region from a to b. For all of these things we are handling the maximum value of the function. And then the Simpson method, the error of it is at most equal to b minus a to power of 5 over, these are some peculiar numbers that we cannot really justify right now, b minus a to power of 5 times over n to power of 4 times the maximum of the fourth derivative, again on the area from a to b. So in some cases, in some advanced examples, you might want to get an estimate on your error, and these formulas help us to do that. Okay, guess I'll stop the lecture here, and we are going to start a new chapter altogether on the next lecture. Until then, good luck and God bless.